All right, so our next speaker is Adam Petz. He's a PhD student in computer science at the University of Kansas under the guidance of Dr. Perry Alexander. Adam is currently working under the Cyber Assured Systems Engineering DARPA effort, and he's going to talk about a Copland Attestation Manager.
Thank you for the introduction. And my name is Adam Petz, like you said, and in this work, my co-author is my advisor, Dr. Perry Alexander. And I'd like to talk about our prototype implementation of an attestation manager that is built on the Copland framework. Now, the Copland effort is joint work with our partners at the NSA, MITRE, and Johns Hopkins APL. And all of their names are listed here. And there are a few here in the audience today, so they can heckle me if I get things wrong. So a quick overview of what I'll be talking about today. So I'll do a little bit of background on remote attestation and the Copland framework itself. And the goal of the Copland effort is to provide new ways to write, analyze, and execute attestation protocols. And our prototype attestation manager work focuses more on the execution part of that effort. And so I'll talk about some of our implementation decisions there. And then I'll also talk about some ongoing work in that area. So I recently gave an overview of my research to an interdisciplinary audience at my university, and I started with some motivating slides that showed some scary screenshots of malware and some scary statistics about the number of millions of users that have been affected by data breaches caused by malware. But after talking with my advisor, he assured me that the audience here would be well aware that scary things happen to computers. And so I'd like to go ahead and instead just dive into the technology that can combat malware, or at least detect malware, and that is remote attestation. And the goal of remote attestation is to provide a way to reliably collect and report the state of software executing on a system. And so it typically involves an entity called an appraiser that makes an attestation request to a target platform and asks for that target to provide some kind of evidence as to its trustworthiness. And then the appraiser will evaluate that evidence against its own standards. Now, the appraiser would like the evidence to reflect the current state of the system and not some past state of the system. And the appraiser would also like to know as much as it can about that target platform. So that takes care of the first two principles here, fresh information and comprehensive information. And I should mention that these 5 principles listed here come from a seminal paper in the attestation literature called Principles of Remote Attestation. And as we've been building these types of systems and looking at ways to verify them, we've kind of kept these design goals in the back of our mind. So the third principle is constrained disclosure, and that says that the target may have some privacy initiatives on its own that it may not want to divulge its entire configuration. So a reason for this might be if the target has an unpatched vulnerability that it doesn't want the world to necessarily know about. And so there's some inherent conflict between principles 2 and 3 here, because the appraiser wants to know as much as it can about the target, but the target also wants to protect itself. So this is a big challenge in these types of systems. The fourth principle is semantic explicitness, and I think this is the most relevant property to the Copland effort, and we'll see later how the Copland language will kind of embody and give us a way to have a uniform semantics for attestation so that appraisers can collect evidence from multiple attestations and compose them and to make more informed trust decisions. And the fifth is trustworthy mechanism, which says that we have to trust the attestation mechanisms themselves. And although our prototype implementation doesn't tackle this solution completely, I think that we do start to explore some of the design space and at least identify some of the components that need to be trusted in these types of systems. So here's the Copland language itself, and it has a number of language primitives, and the first type of language primitives are system measurements. And there are two types of abstract system measurements in the language. The first is a USM, or user space measurement. And this can be anything from the hash of a binary of a virus checker running in user space, or it could be as complex as a very complex snapshot of the runtime memory of user space. And we leave user space measurements abstract in the language, but we do provide a way to specify input arguments to these measurements to specify what type of measurement you'd like, and also if it has parameters, you can pass those in as well with this argument list A. And of course, to measure a virus checker binary, you rely on many services of the underlying components, like the operating system, that are sort of in the context and are necessary to measure the virus checker itself. So we also have a different kind of system measurement called a KIM, or a kernel integrity measurement, that takes an additional parameter P to specify the place at which you'd like to measure the kernel. So this is one of the terms in the Copland language that allows us to kind of extend trust in the system and allows one domain to establish trust in a kernel of another domain, which can then facilitate user space measurements on that platform. Next, we have measurement sequencing operations. And I'll talk about these in detail more later in the presentation. But at a high level, they are ways that we can compose and enforce some sort of ordering on measurements of the system. Next, we have cryptographic operations. So our three abstract cryptographic operations are digital signatures, hashing, and copying of data. So these operations act on the evidence produced by these protocols. Next, we have remote requests. So the @pt term allows an entity to request that a protocol T be run at a remote place P. So this is another way we extend trust across domains in the Copland specification. And finally, we have evidence types, which represent the results of protocol execution. So Copland has two types of formal semantics. The first is an operational semantics, which describes step-by-step how these protocols evaluate to evidence. The other type of semantics is an event semantics, which describes or asserts that certain system events occur before or after one another. So examples of types of things that might be system events are like communication events, like sends and receives. It could be system measurements, and they could also be cryptographic operations. So this diagram on the right shows some system events for a particular Copland phrase. And so there's an upcoming paper in the post conference that describes the formal definition of Copland and its semantics. And the main formal result of that paper states that some kind of relation between the operational semantics and the event semantics. And that result says that whatever execution happens in the operational semantics is sort of reflected in the event semantics. So that, and what that means for people implementing these systems is that if we model our implementation off of the operational semantics, we can have some guarantee that the things we verify about the event semantics actually hold true for the implementation. So we are exploring many ways to analyze these attestation protocols, and a particularly enlightening way is work by Paul Rowe, who spoke yesterday about characterizing the observability of effects in cyber physical systems. But in this work, he makes the very reasonable assumption that attackers are going to corrupt system components. So in our experience, we've seen this is true. They know how to corrupt the components. However, if we can incorporate these corruption events here in this diagram, the red events, if we can incorporate these attacker actions into events that are derived from Copland specifications, we can give the protocol designer sort of a candidate list of measurement strategies that they can choose from in order to ideally force the attacker to perform more difficult attacks. And so one of the main results from Paul's paper, the paper is called Confining Adversary Actions via Measurement. One of the main results is that we know how to choose measurement strategies that either force the attacker to perform a deep corruption, which is ideally a more protective component in the system, or perform an attack that is very time sensitive and requires the attacker to perform the attack in a very short time window. So moving away from the formal semantics of Copland, I'd like to talk about our prototype attestation manager. And although the title calls it an attestation manager, I like to think of it as more of as a language interpreter. And so here we can see the high-level structure of the interpreter itself. So starting from the left, we pass a Copland term and some initial evidence into the interpreter. And the interpreter dispatches system measurements and crypto operations to its host system. And when it encounters an at term, it then sends that term as a request to some remote attestation manager that we assume is running in some other domain. And when the entire term is processed, we get evidence out, and then the initiator of that protocol can evaluate that evidence to its own standards. I will mention that we also include a JSON evidence wrapping in order to give a more language agnostic way for these protocols to communicate with, or for these platforms to communicate with one another. So here is the interpreter. I was pretty proud that I could get the entire interpreter code on one slide. It is a little bit misleading because there are some helper functions that hide some of the complexity, but it gives you kind of an idea of the structure of the interpreter. So here on the left, we have a data type that represents Copland terms. I will mention that the only difference between our representation and the formal representation is that we've actually added a nonce primitive, and we've also added, for the system measurements, we've added an ASP ID, which is an Attestation Service Provider ID. And so we could have definitely encoded a nonce as a user space measurement. And similarly with ASP IDs, we could have encoded them in the arguments that we supplied to the USMs and KIMs. But I think this implementation is a good kind of testing ground for language extensions to see how we might bring those back into the formal spec and if it's easier to code these protocols with these extensions. So I mentioned earlier that there are ways to sequence system measurements in the formal specification. So I'd like to talk a little bit about each of these three ways to sequence measurements and sort of their utility, and also how we implement these and how it corresponds to the formal specification. So first we have linear sequencing of measurements, and this is represented in the formal semantics by the arrow operator. And this says that a measurement T1 should happen strictly before a measurement T2. And so in the formal diagram below, you can see this represented, and we have our interpreter code above it here. And so I'd like to kind of highlight how the formal spec corresponds to the interpreter. So here we have initial evidence E that's passed to a T1 measurement routine that produces evidence E1. Similarly, we have evidence E1 that is input into term T2 and produces a result. However, the formal specification also says that it provides an ordering relation on these terms. So T1 must finish its measurement before T2 starts. And so each interpreter that we write for these terms must have some way of enforcing that. And so we're using the language Haskell for our implementation, and Haskell happens to have an operator called pseek, which the semantics of pseek says that its first argument must be fully evaluated before we evaluate the second argument. And since Haskell is a lazy language by default, which means that it essentially will evaluate arguments as needed, we force that E1, the result of the first term's execution, be fully evaluated before we even start the second one. So although this is sort of an ad hoc choice because of our choice of language, implementation language, I think it highlights the need for such a capability in any such implementation. Next, we have the branch sequence measurement operator, and it also performs measurements T1 and T2 in sequence, but the difference here is that we supply a evidence splitting function, pi, which branches evidence to the different subterms. So we don't have to use the same input evidence for both terms. And the specification also says that these must happen in sequence, so again we see the pseq operator in the Haskell implementation. Finally, the third and final way to sort of sequence measurements is the parallel operator. Here we also split evidence between the two subterms, but notice there's no pseq in the implementation, so the different branches are free to evaluate these or perform these measurements in any order. So in order for our interpreter to interpret system measurements, it has to have a way to dispatch these measurements based on their measurement ID. And so this interp USM function takes an ASP ID as an input, and in this example, we've chosen ASP1 to mean hash a file. So you can see there's logic here to grab the first argument of the input, and that argument should be a file name, and we go ahead and hash that file. But you can imagine a long list of these ASP IDs as we add more measurement capabilities to the system. So I mentioned that the formal semantics has a notion of evidence, and I would say that it was more aptly named an evidence type. So the formal semantics captures the structure of evidence collected by these protocols, so how they are sequenced, how they are bundled into signatures and things of that nature. But for the formal semantics, for the implementation, we need ways to represent concrete measurement results. And so things like hashes and signatures, they return bytes. So we need a notion of bytes in our implementation, and I've named this data type BS here, and I didn't name it that because I didn't include a definition on the slide. I named it BS because it stands for byte strings. And so I think this concrete evidence highlights the need for a way to collapse this evidence when we would like to perform crypto operations on it. So for instance, before we sign a piece of evidence, we need to collapse it into its binary representation and take the signature over that data item. And so it's very important that different instances of this interpreter share a notion of how to collapse data before performing these crypto operations. And we've chosen one particular strategy where we simply grab the binary parts of the evidence, ignoring all the different evidence tags and whatnot, and then append these binary bits into sort of a long string of bits before signing the whole package. But regardless, any such interpreter needs a way to bundle this evidence. I wanted to show one example of how we represent Copland terms and evidence in JSON. So this is an example of the result of a kernel measurement as a JSON object. And there's not too much going on here. I should say that one interesting choice we made was, I don't know if you're familiar with JSON, but there are basically three types of objects you can use in JSON. You can use numbers, strings, and objects. And so in order to represent binary data, we had to sort of choose a way to encode binary data in the existing JSON infrastructure. So we just chose to use base64 encoded strings. Really quickly, I'd like to talk about some implementation quirks. So we have a couple of different communication modes. The first is a shared memory mode, in which each node shares an environment and has mailboxes. And we found that this mode is pretty convenient for testing because we don't have to go around and start up each node individually. We can sort of control the execution from one location. And But a more realistic mode of communication is our socket-based mode, where each node has its own environment and listens for requests on specified ports. Another type of mode is our simulation mode, where we can, if we'd rather not perform actual crypto or system measurements, we can fake them and focus on the parts of the interpreter that are bundling the evidence. And so this is a great tool for testing and for getting results back quickly from our attestations. We also have the real mode that performs the actual crypto and system measurements, and this allows us to do meaningful appraisal on this evidence. So we have some ongoing work in this area. First, in the formal verification category, one of my advisor's other students, TJ Barclay, is working on ways to translate our current prototype interpreter into a language called KML, which is a subset of the ML programming language with a formally verified semantics. And KML has a formal proof in the Hall theorem prover that says that any program written in KML is compiled to a semantically equivalent assembly language program. And so what TJ is doing is translating that formal specification from Hall into Coq, which is the theorem prover that we have used for the formal results in the Copland effort. Next, we're looking at ways to extend the Copland language, so adding things like Lambda functions and macros and making it easier to write these protocols, looking at ways to add nonces and keys explicitly in the language, also looking at ways to perform multiple Copland attestations and interleave them. So right now we can get an evidence result and appraise it, but we can't necessarily perform more stateful protocols that rely on multiple interleaved executions of these things. And we'd also like to look at trusted hardware and how we can integrate that into our infrastructure. Finally, target platforms are we currently support Linux, but we're looking at ways to extend these platforms to Windows and the Cell4 verified microkernel as well. That's my time, so thank you. If there are any questions.